One announcement. Okay, so the assignment number 7 is out, right? So that is due in 1 week. That is about very interesting assignment. I'd like you to design a digital watch. Okay, digital watch. Your watch using timer. Okay, so timer will be timer interruption. We already studied private timer right before, but I'd like you to use here timer interrupt to design digital watch. Okay. So every 1 second timer interrupt will be generated. Then you can increment second. Right? So every 60 seconds you can increment the minute and so on, right? Like that. So timer interrupt will be studied today, right? So after today's class, you will get some idea how to do design digital watch. Okay, so that is one. Okay, any question before the class? Anything you want to say? Again, don't be shy, right? Don't be shy. Okay, today's class will be super important. Every class is important, but very important. We are talking about two important events in computer system: interrupt and exception, right? Interrupt and exception. And again, interrupt can be classified into two: hardware interrupt and software interrupt. So last time we studied software interrupt instruction as GIC and exception too, right? So one example of exception: undefined instruction. So today we will talk about this hardware interrupt. So hardware interrupt is generated from I/O devices like timer, UART, keyboard, mouse, this is spotlight, any I/O device, right? I/O device that is generated from I/O devices. So we will study hardware interrupt today. Okay. So take a look at this computer system block diagram. You have CPU memory connected through this bus, address bus, data bus, and you have many different I/O devices here. I listed only timer, UART, what is this? Network interface card for Ethernet communication, and this graphics card and sound card. And every I/O device has one output, generating one output, that is interrupt. Some event happens. If I press this spotlight, there is an event. If you type keyboard, that is also event. You move your mouse, that is an event. Network packet comes in, you type CNN.com. Then your request packet goes to CNN server, and the response packet comes in. There is an event, right? Computer system received a packet from CNN.com, then generate an event. Right? So every I/O device is generating an event that is called interrupt. Right? That physically you have at least one, not at least one output connection, and somehow you want to connect these many different outputs to the CPU. Right? Somehow you have to physically connect that output, timer output, UART output, NIC output, and so on, that output to CPU input. Right? So how would you connect? Let me ask you a question. How would you connect this output to the CPU? There are many, and just one incoming, one connection to CPU. How would you connect? What kind of hardware component would you use? Digital logic. And hardware component would you use? Connect that guy into probably obvious way to connect these two CPU is using OR gate. Very simple to connect like this. How about that? The OR gate, right? So what is the OR gate? Any of the input is one. Any of the input is one, and output is one. Right? That is the OR gate. Right? So OR gate. So any of the input is 1, right? It is a circuit. So let's say it is connected to timer. Okay? So some event happens, countdown happens, right? Decrementing to 0, then event happens. Then line got a circuit, 0 to 1. Then this line also 0 to 1, right? That goes to CPU. CPU interrupt. So CPU can recognize that event, then do some processing. Simple, right? Very simple to understand. Easy, simple to understand, and it makes sense. But people don't use that simple OR gate. And that is typically replaced by very special hardware component called interrupt controller. Okay? And why do you think so? What would be the problem with this connection? Let's think first about the connection. What would be the problem with the connection? Yes, very good point. Yes, right. So interrupt happens, right? Let's say timer is connected to that input, and UART is connected to that input, and so on. Many different I/O devices are connected. Then somehow interrupt is generated. Interrupt is generated by one of them or several of them. Then that line got asserted. Then CPU gets interrupted, and the first thing you have to do is you have to figure out who generated the interrupt. Then how would you find out? What would you do to find out who generated the interrupt? Let's say UART, GPIO. Let's say GPIO. That is connected to switch. So you press the button, an event happens. Right? So that is connected here. Then what would you do? CPU, it is jumping to ISR, right? Interrupt service routine. Okay. Jumping to ISR, executing some code. And at the beginning of the code, probably you have to figure out who generated the interrupt. What would you do to check out the I/O device generating interrupt? What you do is every I/O device, right? If you remember the lecture, I/O device lecture, every I/O device has a register called status register. So as I/O devices has 3 kinds of registers. First one, configuration. Before you use I/O device, you have to set up operating condition, right? Before normal operation. Configuration register. Second, data register for normal operation. The last one, status register. So timer has a status register, and UART has a status register. GPIO has a status register, and so on. Every I/O device has a status register, and that event information push down the switch. Then that event information is recorded in status. Some bits in status register. So what you have to do in software, in ISR, you have to read. You have to read a status register in every I/O device, each and every I/O device. So what you have to do is in ISR, you have to execute what? LDR instruction, memory read instruction, because those registers are memory mapped. Okay, so read the register, read probably R0 from some location, R1, and location is that. Location is R1. Then you check out, okay, R0. Then you have to compare. R0 is equal to some value. Okay. If not, then you have to check out. Okay, you read. This is that status register. LDR R0 probably R. I don't know. Some R2. I don't know. The location of that status register. Okay. So if that guy did not generate interrupt, then you have to check out this guy. Okay. Let's assume that you have 1,000. You have 1,000 I/O devices in your computer system. Then in the worst case, the last guy generated interrupt, you have to fork. Okay, you did that, or you did this, you did one. The last one, right? Last one generated finally. You figure out, okay, you are the criminal, right? You did generate, you interrupted me, right? So the problem is what then? You can figure out who generated the interrupt, but the problem is, issue is what? Issue is performance, right? It takes too much time. Latency, response time, interrupt response time. That is called the latency, interrupt latency. Right? Interrupt latency is simply too long, too long. Right? So with that simple hardware structure, you cannot design a system like real-time system, real-time embedded system, okay, real-time. Real-time embedded system means some event happens, CPU should respond immediately. Like the system in car, brake system. Right? You press the brake, then car should respond immediately. Let's say car says, okay, I have to check out this car. You have to wait, then you are dead, right? 1 millisecond, right? Then you are dead, right? And also pacemaker, how about that? Pacemaker in patient heart. Okay, you have to beat the heart at regular some interval, right? Then computer system says, okay, I'm busy. You have to wait, then you are dead, right? About anti-ballistic missile, right? Something like North Korea is firing missile, right? Firing missile, and you want to destroy it, right? With anti-ballistic missile. So there's a computer system. It's supposed to be real time. So probably 1 microsecond. Every 1 microsecond, you have to. This computer system should compute new location. It is changing direction and location super fast. Anti-ballistic missile. So computer system should compute the location and direction real time. So you miss the deadline, 1 millisecond deadline, then you are missing. So real-time system, okay, very important, interrupt latency. Okay. So we cannot tolerate that slow performance. Okay, we want to know immediately who generated the interrupt. Okay, so people don't use this one. And another issue, what do you think? There is another issue. What do you think? What do you think? What is your name? Day? Day is not you, right? You are Day. Okay, I know you, right? With face mask. What do you think? Anyone? Any other issue with that other configuration? Yeah, I think you're correct. I cannot hear you correctly, but I think you're right. What if 2 guys or 3 guys or 5 guys generated interrupt at the same time? So your timer, okay, time. This is time, and this guy generated the interrupt, and you are generated the interrupt. That guy generated the interrupt at the same time. Who do you want to service first? That can happen, right? These IO devices are operating simultaneously at the same time, right? While I'm moving my mouse, right? Timer may generate the event, count down to 0, right? And you are communication, right? Network communication, right? So event can happen at the same time. Then who do you want to service first? Who? The guy? So why then? Why do you want to service that guy first? You have to assign priority, 우선순위 in Korean. Okay? Probably that guy is important. Okay, so timer is, I think, priority number 1. Priority number 1. Okay, that guy is important. If event happens at the same time, I want to service that guy first. And this guy is next. Priority number 2. Priority number 3. Something like that. So you want to implement priority mechanism because there are many IO devices they can generate interrupt at the same time. Right? And then how would you implement priority mechanism with this simple OR gate? What do you think? How would you implement? So hardware is provided, hardware is fixed. So somehow you have to implement priority mechanism in software. You cannot change hardware, right? Hardware is fixed already. So how would you implement priority mechanism in software? Can you please speak up? Load, yes. You want to check that guy first, right? Check this guy first. Check status register first. And check status register next. And this one third. Right? If the priority is highest, then you check this guy first in ISR. Interrupt service routine. But with that scheme, still there is a problem. Still some problem. What do you think? Anyone? I keep asking questions. Anyone? What would be the problem? CPU is executing your hello world application, and let's say timer interrupt happens here. Timer interrupt. Then you are supposed to execute timer interrupt service. Okay. And come back. Then you decided to allow nested interrupt processing. Let's say nested interrupt processing. So many I/O devices, right? While processing ISR, then if some urgent and higher priority interrupt happens, I want to service that guy, even though I'm in the processing of the current interrupt. So let's say you write CPS, change processor state, interrupt enable, even though when you're making transition, CPSR, IBIT set to 1 by hardware. Hardware is setting. That means while processing interrupt will be blocked. CPU will not take interrupt. CPU is not taking interrupt, right? CPU, CPSR, IBIT. That is blocking IRQ incoming. That interrupt. Right? So then you don't like that interrupt blocking. So using CPS instruction, interrupt enable, then IBIT. Then you are clearing that bit. That is clearing CPS R IBIT to 0. That means you are now taking interrupt. What if you are generated the interrupt in the middle of executing ISR here, generated UART interrupt generated. Then that UART interrupt will be taken by CPU. There is nothing prevent CPU from not taking that interrupt because it is simply connected. That interrupt is forwarded to CPU through that connection. So nothing prevent CPU from not taking that interrupt. Even though UART, look at this, UART has the lowest priority, and this one timer is the highest. So you are supposed to finish timer interrupt processing first, then UART processing next. But priority got reversed in this case, right? Even though you are processing timer interrupt, then you jump to UART ISR, UART handler, right? Then you jump back. That means you are servicing UART interrupt first, then timer interrupt next. So we don't like that, priority inversion. Something like priority inversion, right? Does it make sense? Does it make sense? Any question about this? Yes. No. Okay, so the question is, I think, when this signal got asserted, right? and the signal is supposed to be pulled down at some point, right? That is a question, right? So what do you think? In timer case, if you remember private timer status register, you have what? You have sticky bit, remember? Countdown happens, right? From 100, 99, then 0. Then that sticky bit is set to 1 by hardware as a status register. Right? Then at the time, the line will be raised. This line. Okay. Then using software, you are supposed to clear that bit. If you remember, private timer, right? In ISR, you are supposed to clear that sticky bit by writing value, right? You have to use store instruction. So R0, right? Let's say it has 1, right? Then status register R1. So you are writing 1, 1, 2, that sticky bit. Okay. Then at the time, that line will be pulled down. So the point is very good point actually. In the interrupt processing in ISR, you are supposed to touch. You are supposed to touch I/O device. You have to inform I/O device that okay, I'm done. I'm done processing your request. You have to write that program. You have to write that code in interrupt service routine. The GPIO generated interrupt, and at the end of interrupt servicing, you have to inform. You have to tell GPIO, okay, I'm done. I'm done processing your request. That is achieved by programming status register, updating status register. So that line will be raised down, put down. A very good question. Any other question? By the way, does it make sense? Okay, that is why people don't like that simple connection. So instead, that is replaced by very special hardware called interrupt controller. That is providing some advanced capability to reduce interrupt response time. The response time, right? You have to, okay, who generates interrupt, right? Reduce interrupt response time. Second, to implement priority mechanism. Okay, that is the purpose. Using interrupt controller, you want to do fast processing of interrupt and efficient processing of interrupt. Fast and efficient processing of interrupt with that interrupt controller. This one, Dave, can you please? Okay, first, terminology first. Depending on company, depending on CPU company, depending on embedded system, hardware design company, there are several names to refer to the same component, interrupt controller. Some company use advanced programmable interrupt controller. Some company use just PIC, programmable interrupt controller. Some people say just interrupt controller, INTC. There are several names. And in ARM, the one we are studying, they are using this name, generic interrupt controller. Generic. So names are different, but functions are super similar. Priority mechanism, fast response time. Some company says intelligent interrupt controller. Just a name, right? Their name, advertising, marketing. Okay. So there is a name, and you want to implement priority mechanism, some intelligent management for fast response, reduce interrupt latency, okay, and better management, priority management. Okay. Let's talk in detail. So before that, there is x86 based computer system block diagram. Take a look at this. How many interrupt controllers are there in your desktop or notebook computer system? Okay. So here it is server, little bit old server system, and 2 sockets. Right? So 2 processors can be inserted here. Socket 2, 4, i7, 2 sockets. And chipset, two big chips. So inside this chipset, you have 2 interrupt controller called 8259. This is very super old interrupt controller, more than 40 years old. Let's click on this. Okay. So there is a data sheet. Here, let's keep. Okay. Okay. So this PDF document. So take a look at this. This is really pretty old interrupt controller. So it is able to take it by looking at this block diagram. Okay. By looking at this block diagram, it is able to take. That is input. IR0, IR1, IR2, IR7. Those are inputs. 8 interrupt inputs. So that means you can connect 8 I/O devices here. 8 I/O devices, and then aggregating those 8, then there is output INT. 8 inputs. So 8 inputs and 1 out. You can connect only 8 I/O devices. Okay, with 8259. Pretty old. And you have not only that 8259, but you have inside the chip you have another interrupt controller called I/O advanced peripheral interrupt controller. Not only that, you have two more interrupt controllers inside processor, local AP. So it is a little bit complicated, really complicated. The point is, every computer system has at least 1 interrupt controller integrated. At least 1. Intel is super complicated. Don't worry too much about that. Right? So I don't want to show. Computer system has interrupt controllers. Okay, let's talk about our interrupt controller in Cortex A9. Okay, this one. Harima, please. Okay, thanks. Interrupt controller, generic interrupt controller. That is the one we are going to study. And ARM is upgrade the interrupt controller from version 1 to version 4. So we are going to study this version 1, first version. Okay. Version 2, version 3, version 4 contain same capability as version 1, but added some more functionality. So this one, the function in GIC version 1 is applied to other versions as well. So that is good. Okay, this one is system block diagram, very confusing. So I color coded here. This pink are interrupt sources. You can think of it as I/O devices. This pink, right? So you have, for example, a private timer here. Okay, and you have UART in this pink box, and GPIO in this pink box. Okay, and that is interrupt is generated, then that is connected to that module, hardware component. This one is called the distributor. Green is called distributor, and here we have CPU interface module. Two big modules. First one distributor, green, and purple CPU interface in generic interpreter. Let me show you. And, a little bit confusing at first. So let me quickly go over PowerPoint and use this whiteboard to explain the example. So here, pink again, interrupt sources, I/O devices. Here you have a private timer. Here you shared I/O, right? Shared peripheral. That means I/O. Peripheral is I/O. Here you have UART, GPIO, USB, some I/O devices. That is connected to distributor. Right? Look at this. Distributor. And this purple is CPU interface. That is hardware component. We're talking about hardware component. So, okay, so let me show you. So a little bit confusing. Just to follow this PowerPoint slide. So let me show you this and use whiteboard to explain. Okay, let's read this. Okay, there are two big modules in GIC, generic interrupt controller, distributor and CPU interface. This one, can you please read distributor? One, please. Done? Okay. Okay, thanks. So if you go to our class page, then you can find out the reading assignment, right? So the PowerPoint was created based on this documentation. Take a look at this, GIC architecture specification. Generic interrupt controller documentation explaining about that hardware, right? So check out this chapter 4, programmer's model. Then 4.1 distributor, right? So distributor, that is listing the registers, distributor contains. So at the end of the day, what you have to do is you have to touch registers. Distributor is provided. You have to touch using software. I'm talking about software. Using your software, you have to program those registers. And you have to program, that is in, those registers are inside distributor. And if you scroll it down, CPU interface. Okay, there are registers. These registers are provided. So what you have to do is you have to program those registers. That's what you have to do. But because there are so many registers, sometimes you get lost, right? Pretty complicated at first, right? So let me explain with whiteboard, because PowerPoint slide is not that good to understand. So let me draw hardware schematic diagram first. You have distributor. There is TOR or ER or OR? OR or ER? OR? Ariman, what is correct? ER or I don't know. Okay, anyway. And really bad at spending. You have CPU interface. Okay. And that is specific to one CPU. CPU 0. And then CPU 1. And you have separate CPU interface module. That is 4. Here, that is IR2. This one is IR2 and FIQ. And this one CPU1, ARM CPU. So IR2, FIQ. Fast interrupt. And you can have up to 8 CPUs in GIC. Number 7. So you have CPU interface. I don't want to do it. So that is block diagram. So distributor, as the name implies, right? So interrupt coming in, input. So for example, private timer. Timer is generating interrupt. That is, interrupt line is connected to distributor. Okay? And USB interrupt is connected to distributor and GPIO connected here like this. So ARM is doing what? ARM is doing IP business, intellectual property business. So ARM architected this generic interrupt controller. That is generic. That is GIC, generic interrupt controller. So when ARM architected generic interrupt controller, they had multiprocessors in mind. So you can have up to 8 CPUs in your system. Again, ARM is doing what? ARM is doing license business, right? ARM is providing this intellectual property, and they are selling this intellectual property to Samsung, LG, Hynix, Intel, Qualcomm, you name it, right? They are doing IP business, intellectual property. Okay. So once you purchase a license, let's say Samsung, right? Samsung purchased their license, then you can customize it. But their baseline. Okay, so you can have up to 8 CPUs. But in your application, if you don't need 8 CPUs, then you can remove. Okay, I don't need 4. I can have only 4 CPUs. Or okay, I think 2 CPUs would be enough. Okay? You can customize that intellectual property. Okay? So anyway, they are providing this template, the GIC structure. In this baseline, in this base GIC, you can have up to 1020. You can connect up to 1020 IO devices. Let's say IO devices. You can connect up to 1020. But if you don't need that many connections, let's say you have only 96 IO devices. 96. I have only 96 IO devices. I don't need that many connections. That is okay. You can customize it. Customize that intellectual property to connect only 96. Okay. GIC has 96 connections. Okay. And the important thing is, okay. So with that connection, what you want to achieve? What you want to achieve is So CPU, okay. Let's say only you have one CPU. You have only one CPU. You have distributor module and CPU interface and our CPU server. Then your CPU is processing your application. Hello world. Then interrupt is generated. Right? Then what you want to achieve is there is a separate handler, interrupt handler. Right? So for example, timer interrupt handler. Right? Software program, software. Okay. Some handler, then USB, right? USB handler. And then GPIO handler. Separate program, right? For each IO device. Okay. And interrupt happens, then what is happening? So ARM is referring to interrupt vector table. Then jump to, let's say this one is IRQ, ISR, IRQ. Right? Coming in, interrupt is coming in. Let's say interrupt coming in through this line. Then you have IRQ handler, right? IRQ, ISR, interrupt service routine. So CPU will refer to this table and jump to IRQ, ISR. So first thing you have to do is what? Okay, you want to do, okay, who generates the interrupt? You have to figure out. Then, based on that, you want to jump to here or there GPIO. That is what you want to achieve. What you want to achieve, right? There are separate interrupt handler for each IO device, right? Timer handler, USB handler, GPIO handler, Wi-Fi, Bluetooth handler, and so on. Many different handlers, right? So you have to figure out who generates the interrupt, then jump to that handler. That's what you want to achieve, right? That is the final goal. You want to achieve with that interrupt controller. You want to do it fast. You want to jump there fast, jump there fast. That's what you want to achieve, okay? And as a distributor, right? So let me talk about distributor. The main function of distributor is what? As the name implies, distributor. You want to distribute it, right? Because there are ARM had multi-processor in mind, right? So interrupt happens, for example, USB interrupt. Then distributor, you want to make decision. Okay, who do you want to service that interrupt? Okay, that guy or this guy or that guy? You want to distribute it. Okay, distribute, right? Interrupt. Okay, for example, USB interrupt. I like USB interrupt to be serviced by this guy, CPU7. I like GPIO interrupt to be serviced by CPU1. I like timer interrupt to be serviced by CPU0. You want to distribute, right? So for that purpose, you need register for distribution purpose. Okay, that is called target register. Target. Who is the target? Target register. Target register is 8-bit. Okay? 8-bit is enough because you have 8 CPUs. 8 CPUs. So each bit is corresponding to one CPU. So if you set this bit to 1, let's say if you set this bit to 1, okay, then you want to send, for example, timer interrupt to CPU 0. If you set this bit, the last bit, MS bit to 1, okay, then you want to send that in some interrupt to CPU 7. Simple, right? But one 8-bit register is not enough. There are how many? 1020 interrupt sources. So that means you need 1020 target registers, one for each, right? This one is for this one, second one, this. The last one, we have to program each this one. It makes sense, right? So one target height for each interrupt source. Okay, and each interrupt source goes by its unique ID. The ID is already fixed. For example, timer interrupt, private timer. This one is important. Private timer. The ID is already fixed by that architecture. See, ARM architecture. Number 29. This one number 0. 29, and the last one is number 10, 19. That ID is already fixed. So number 29 is assigned to private time. The computer is processing ones and zeros, right? Not character. So you have to use number 29 for timer. Okay. Some interrupt USB. Let's say, let me show you the table. Look at this table. So it is showing ID number. So for example, number 54, that is assigned for Ethernet IO device. Number 53 is assigned to USB. 52, number 52, assigned to GPIO, and so on. So each IO device has its unique ID. Unique ID. Each IO device. So now we are going to use that unique ID. In the demo program, we are using this private time. So you have to remember number 29. Okay. So the first one, okay, again, let's go to this. The first function you have to implement in distributor is target register, because ARM architect has multiprocessor in mind, ACPUs. You want to distribute it. You want to send IO interrupt, specific IO interrupt to some CPU. And the second important register is priority register. Same thing goes to here, right? Priority. GIC assigned 8-bit register for specifying priority for each interrupt source. So number 0, for example, you can say, okay, I want to assign priority 5, for example, for interrupt, for this interrupt, this line, number 0. And then you should have 1000. You should have 1020. You should have 1020 8-bit registers to specify priority for each interrupt source. So again, for 29, you have to touch. Let's say number 0, number 1. Then 29. You have to touch that register. Okay? To set priority for private time. So in the demo program, I set priority 10, 1, 0 in hex. 1, 0 in hex for private time. Okay, so far so good. Priority. So important function of distributor is specifying target. That is the first one. And second, setting priority of each interrupt source. Okay, not that hard, right? Okay. So then that is the main function. But separately it is providing enable capability, enable of each interrupt source. Okay. So enable register. Okay. So for example, okay, I want to take that interrupt. I want to take this interrupt. but I don't want to take that interrupt. You can enable or disable. And 1 bit is enough. 1 bit. Enable, disable, right? 1 bit is enough for each interrupt. So enable. You have register is 32-bit in size. 32-bit enable register. So the first bit is for ID number 0. The last bit is for ID number 31. Then how many enable registers you should have to cover 10, 20 IO devices? For simple math, let's change that to 10, 24, because we are familiar with the number. That is 2 to the power of 10. 4. This one is 4 shy. 4 shy of 1024. It's very close, right? So then, how many registers you need to cover 10, 24? 10, 24 interrupt sources. 32. Divide by 32. Then you need 32 registers. 32 registers, right? 32 registers, 32 enable registers. Okay. Okay, 20. Okay. Still have time. Then one more thing. Okay. Again, register is 32-bit in size, right? 32-bit enable register, and target register is also 32-bit in size, not 1 byte in size. So that means 4 registers. Is 4. 1 register is holding. Target 0 register, for example. Target 0. That is holding these 4 bytes. Okay. And next 4 byte, okay, is located in target 1 register. Because each register is 4 byte in size. This one target register is 4 byte. Okay, these are 1 byte, 1 byte, 1 byte, 4 byte. So each register. Same thing goes to this priority register. Right. So 1 register is 40. 4. 1, 2, 3, 4, 4. Then you can figure out, how many registers you need to specify priorities for all 10, 20. So that is why so many registers in GIC. Okay, that is one. And then we are almost done. There is a distribution. Okay, again, target register, target setting, priority setting of each interrupt, each input source, and enable or disable. And let's move on to the CPU interface. So based on this setting, interrupts generated, then there is forwarded to CPU interface. And CPU interface, important register, you have to remember, is priority mask register. Priority mask. Meaning you can set threshold. Okay. The thing is this: if that distributor is forwarding interrupt to CPU interface, and if the priority of that interrupt is not high enough, if lower than threshold, CPU interface is not going to forward that to CPU. Ignore it. Let's say I set this one to FF. In the demo program, I set this one to FF. One thing I have to tell you, the number, lower the number, higher the priority. Lower number, higher priority. Okay, so this one 10. This one FF is lowest. So if timer is generating interrupt, that will be forwarded to CPU interface, and this 10 will be compared against FF. The lower is higher, right? So that interrupt will be taken and forwarded to CPU interface. Okay. So the priority mask, you want to set up threshold. Right? So if you set 10 for private timer, okay, and enable which one do you have to set? Number 29, right? So you have to enable that interrupt, you have to set what? This one ID 31. So this one for ID 30. This one for ID 29. So you have to touch that bit. You have to set this bit to 1 to enable this private time. Okay. So to enable that, you have to set this specific bit. 29 step. 0 step, 29, 30, 31st. Okay. Then that will be forwarded to CPU interface and threshold. So again, if the threshold, right, if the interrupt priority is higher than this threshold, then forward. And then there is one. The interrupt will be generated through that IR2. Then what do you have to do? What you have to do in here? In ISR, you want to check out who generated the interrupt, right? So in CPU interface, there is another very important register called interrupt acknowledge register, IAR. This one is acknowledge. Okay. So interrupting is forwarded from distributor to CPU interface, and ACK register will have the ID, who generated the interrupt. In this case, the private timer generated interrupt, it will contain 29. So in ISR, what you have to do is you read the acknowledge register. Read interrupt acknowledge register with LDR instruction, right? Memory read, right? Let's say R0, R1. R1 is the location of IAR. Then R0 register will contain 29. So by looking at this number in your program, by looking at this number, you know, right? You know, okay, private timer generated interrupt. By looking at this, you can jump to this handler, timer handler. So that ID is important, right? Each IO device goes by with that unique ID, each IO device. Then at the end, at the end of interprocessing, time handler. So one important thing you have to do is the CPU interface is providing the last important register called end of interrupt register. End of interrupt. So the protocol is, so how's your protocol? How do I solve the protocol? You should read this one here. You should acknowledge register, and at the end you have to write same number to end of interrupt register. You have to write 29 using software. So here, write end of interrupt register. Okay, using STR instructions, store instruction. What does that mean? That means you are notifying, you are informing, CPU interface. Okay, I'm done processing interrupt. You can process next interrupt and send it to me. Okay. So again, the writing same value to end of interrupt register means you are informing hardware. Okay, I'm done processing your request. Okay. You can send me another pending interrupt if one of these guy generated interrupt, then you send it to me. I'm done processing current interrupt. So that is a protocol, hardware and software protocol. Hardware is providing acknowledge and end of interrupt. In software, you should read acknowledge register to figure out who generated interrupt, and at the end you have to update end of interrupt. The same name. Right? So hardware knows. Right? And one thing you have to remember, what is your name? Huh? Hechang, right? Hechang expectation, right? The line is supposed to be pulled down, right? So you have to, but you have to be careful. You have to be, remember is, before you write end of interrupt, you have to program IO device, that IO device. Update, right? Status register. So it depends on IO device implementation. In case of private timer, you have a status register. Sticky bit. Right? Using software, you are supposed to clear that bit. Right? Before programming end of interrupt. Okay? So that means you are informing to interrupt controller and also that IO device. Two guys. I'm done processing your request. You are notifying that completion to IO device and also that security interface, GIC. Any question about this? That is about GIC function. I think this one is better. You can now read the PowerPoint. Figure out which one. Yes, they. Yes, hardware, right? CPU interface module. CPU interface hardware module will program this register. Okay. Update this register with the one who generates interrupt. In our case, we assume private timer generated interrupt, and each ID is 29. It goes by with this unique ID. Right? So 29 will be used in GIC. So private timer generated interrupt, and number 29 will be recorded by hardware automatically. So you don't have to do anything. Just read IAR in interrupt service setting. Then you can that by who generated. So compare that against the simple OR gate implementation. Simple OR gate. In this scheme, what you want to do is just read IAR, interrupt acknowledge register. By reading one register, who generates interrupt. Fast response time, really fast, right? And also you can implement priority mechanism, right? So if several IO devices generated interrupt at the same time, then how do that? Based on the setting priority register, this distributor will forward the interrupt with highest priority to CPU interface. So hardware mechanism, right? Hardware is implementing the mechanism. Right? So some very efficient handling, right? It sounds a little bit complicated, but it is actually not that complicated, right? So main function is priority mechanism. Target is because we have a multiprocessor system, multi-CPUs. So priority is the main functionality of the interrupt. Okay, let me show you a demo. Okay, so here. Okay, this is the one. You can download this one. Private timer interrupt. Okay, so now take a look at this assembly program. We have our own interrupt vector table. Okay, then main, right? That is initialization, right? We want to do some initialization. Stack pointer setup. So before initialization, I want to disable interrupt. That means I don't want to take any interrupt. I'm doing some initialization. Don't interrupt me, right? So after set V bar, then after setting up stack pointer, then V bar register vector base, because we want to use our own vector table, right? Then you enable. Okay, now I'm ready, probably. Okay, CPU, only CPU, I'm ready. And the GIC setting is separate. Now, some registers you can check. GIC is providing ID register, some version, right? Some version. So you can, by reading this, okay, you can figure out, okay, it is implementing version 1, for example. So simple ID, right? So type, don't worry about this. I'm just reading, right? Don't worry about this. This control register is global enable. So little separate enable. This one is the enable register for individual IO devices. But there is a global enable. You can enable this distributor. That is global control register. If you don't set that control register, then distributor is turned off, completely turned off. To turn on distributor, you have to program the register. Turn on red distributor to make it active. To make it active is four things. Not this individual. So to enable. There's a whole distributor enabled and individual enabled. Check out the data sheet for detail. So that is enable, global enable. Then look at this. Enable register. So I'm doing what? I'm doing 29-bit shift left. I'm doing 29-bit shift left. So do what? To set this register. To set this enable. Because number 29. Number 29. I want to set this. So 29-bit shift left. Okay. Position that, position to. Then priority register. You need to touch priority number 7. Why? Why is that? Priority number 7. Why? Because each register is holding four bytes. So first one is for ID number 0, ID number 1, 2, 3. So that is contained in priority number 0 register. Okay. So next 4 is contained. Next four is contained in priority number 1 register. So if you count, you have to program that. So 10. For private timer. Let me get down. Private. Our private timer. So ID number 29. Okay. So you have to remember 29. That is private timer. And I set priority to 10 in hex. Okay. 10. So that 10. Then CPU interface. Also, you want to the control register. The convention, right? Convention is this one. Register name convention. The registers in distributor start with GIC D something distributor D something. Registers in CPU interface. Generic interrupt controller and C something. Convention, that is convention. C and D. Distributor and CPU interface. So we have a C, okay, and that is making CPU interface active. It's full. You are turning on you are turning on this whole block, whole hardware. Make it active. Enable. Then look at this, a mask register, PMR. Right? Priority mask register. I'm setting a threshold to FF, which is the lowest priority. Setting this one. Priority mask register to FF, which is the lowest. So that means I can take anything. Tell me anything. I can forward either. I'm not doing any filtering. I'm not masking anything. I'm going to forward that interrupt to CPU. The lowest. Okay. Then that is the end. That is the end of GIC setup, interrupt control setup. Then what? I did this, right? Interrupt enable. Then I set up distributor and CPU interface. Then you have to do what? You have to do private timer setup. You have to make it. You have to, before your normal operation, you have to set up. Right? The same code we did last time, right? Remember pre-scaler, enable, auto reload mode, something like that, right? The same configuration. So that means every this time interval, interrupt will be generated. Okay. Okay. Every that time interval load value, which is that one something. Okay. Interrupt will be generated. Then I want to check if timer is running okay by reading counter register. Counter register, just test code, right? Then CPU is doing nothing, just looking. Then every once in a while, interrupt will be generated at every that time interval because it is auto reload mode, right? Count down to 0, then start again. Count down to 0, start again. Count down to 0, and auto reload mode, right? So every that time interval, interrupt will be generated. So let me. So in ISR, okay, before that, in ISR, what is that? I'm reading acknowledge register to figure out who generated interrupt. That is contained in R3. But in this case, I'm not doing anything, right? I'm reading IAR. I'm not jumping to this specific handler for test code, right? We have only one interrupt, so I'm not doing this, right? Just doing that, executing IAR. So in the main, I'm toggling LED, toggling some LED here, GPIO. Then look at this. 해창, as a 해창, asked, that is pulling down. I'm touching status register, IO, right? This is status register to make it 0. Then at that point, the line will go down, interrupt line. The line will go down. Okay? And one more thing, I'm notifying CPU interface that I'm done by programming end of interrupt register. End of interrupt. R3 here. Acknowledge register, right? Reading acknowledge register that is stored in R3. Scroll it down, R3, no update. R3 update, right? So same R3 will be used to update end of interrupt. Then returning back, yeah, road multiple and SUBS with the destination PC. That means you are returning back to interrupted place. Okay, let me download it too. Oh, did I turn the board? Yeah, probably I have to turn the board. Sorry, I have to turn the board. it is already something wrong with. Let me try it again. Oh, working. I don't know. Probably is. Okay, so here, right? So vector table and stop here. And remember, count the timer count. How long? 16 zeros. 16 zeros, right? Pretty long time from CPU point of view. Right? So I don't want to type F5 100 times. So let me set a breakpoint here, right? Let me set breakpoint to, I already set, right? This one, interrupt vector table. And let me set breakpoint here too. Okay. Then press F8. Okay, stops here. Then forever loop, right? You can check out. You can check out registers. Then I want to make sure counter is counting down correctly. So look at R5, R6, R7, right? So press F5. So counting down, right? It's counting down. Right? So I don't want to, type F5 1 million times. So let me press F8. Then eventually it will count down to 0 and stop at here, I think. Let me press F8. Okay, it stops at here because interrupt generated. Right? Then CPU will branch it to service routine. Look at this. I'm reading acknowledge register. So check out this R3 register. R3 is supposed to have what? 29. Okay, press F5. It's 29 in 1D in hex, 29 in decimal. Okay. So then toggle LED, right? Toggle LED. Okay, turn on LED, then clear that sticky bit in private timer register. Then end of interrupt register. Okay, you are informing CPU interface. Okay, I'm done processing interrupt. Okay. Then you are returning back. So here, forever loop. So let me clear that breakpoint. Then press F8. Then what do you expect? If I press F8, then every that time interval interrupt is generated, LED will be toggled every time. So if I press F8, see LED, right? Those LED will be toggled every that time interval. Okay. So I think you are ready to do that assignment, right? Mr. Watch design. So you have a reference code, then what you have to do is every 1 second increment second. Then second becomes 59, then 60, then the 1 minute, increase. And then print out that message to your terminal, your digital watch. Okay. Any question? Okay, any question? Okay, that's it. That's it for today. 이거보다 프라이어티가 몇십 넘나? 같은 거는 체크해서 같은 반드시 체크해서 여기서 오는 것 중에 올 거 아니야. 그거하고 너의 프라이어티가 얘와 비교해서 높으면
제가 이게 타이머 인터벌
아니 우리가 비싼 거죠. 이거 이상이면 세달은 그거 만나서 어떻게 하면 지금 프라이어티 넘버 제로는 제로 레지스터에는 아이디 넘버 제로부터 아이디 넘버 3까지 프라이어티 이건 4개 있었어요. 이에 대한 프라이어티를 세팅했어요. 여기 따라오면 프라이어티 넘버 1 레지스터에는 아이디 넘버 4부터 7까지 나머지 4개 다른 데 이렇게 4개 그다음에 프라이어티 넘버 2 레지스터에는 8부터 여기까지 오면 16까지 29가 어디일까라는 거는 어느 레지스터 여기까지 오면 넘버 7 레지스터 아이디 넘버 32에서 아이디 넘버 28까지 를 홀딩할 수 있어요. 29면 그거 그리면 4바이트 여기 맨 아래 LS 바이트가 28고 요게 이제 프라이빗 이게 29번 두 번째 바이트를 우리가 109 그걸 위해서 8 10을 이렇게 하니까 포지션을 이렇게 요거 그치 30번 16비트를 밀어줘야지 여기다 프로그램을 하려면 16비트를 밀어줘야 이 포지션에 딱 위치를 그치
할 때 정말 왜 프라이어티가 바뀌는지를 제가 잠깐 놓쳤었거든요.
아, 왜 그러냐면 여기서 오면 인터럽트 처리 중에 저렇게 돼 있을 때 여기 보겠습니다. 여기 인터럽트가 걸리면 얘를 통해서 어쨌든 뭔가 처리를 하고 돌아가려고 할 텐데 여기서 또 걸렸어. 인터럽트가 그러면은 프라이빗 체크를 할 수가 없이 그냥 점프를 해버리니까.
아 그냥
타이머 인터럽트가 걸리고
들어오면 그냥 바로 넘어가는 거예요.
그렇지. 왜냐하면 5억이 있으니까
공개하는
이제 여기 5억 5억이 트이기 때문에 뭐 체크하고 잘 수가 없잖아. 그냥
CPU가 들어오는
그치.
대로 바로 넘어가는
이제
거예요.
인터럽트가 걸리면 그냥 CPU한테 알려줘 버리니까 프라이어리티를 뭐 체크할 그런 것도 없이 CPU는 아 인터럽트 걸렸으니까 또 점프해야겠네 또 그거에 따라서 그렇게 하는 거죠. 그러니까 얘가 프라이어리티가 낮더라도 먼저 처리가 될 수가 있으니까 그럼 문제가 생기는 거죠.
감사합니다.